Welcome to our latest video on the topic of halogenoalkanes, preparation, properties and uses. This video is suitable for AS and A-level students. By the end of this video lesson, you should be able to describe how halogenoalkanes can be prepared from alkanes, alkenes and alcohols. You should also understand the intermolecular forces present in halogenoalkanes and how these are linked to physical properties such as boiling points. And finally, you should be able to describe the main uses of halogenoalkanes and why their uses are restricted due to toxicity and adverse environmental impacts. Now we're going to start this video lesson by looking at the different ways that halogenoalkanes can be made. Now halogenoalkanes can be prepared from a variety of different types of compounds, and these include alkanes, alkenes and alcohols. So let's start with making halogenoalkanes from alkanes. If we react an alkane with a halogen at room temperature in the presence of UV light, a halogenoalkane is formed. So for example, if we react methane with chlorine in the presence of UV light at room temperature, we get chloromethane and hydrogen chloride. And this reaction is classed as a free radical substitution reaction. Now a substitution reaction involves the reactant atoms swapping to form products. Now this method is not a great way of preparing a halogenoalkane because you get a number of different products produced. And to understand this, you need to look at the reaction mechanism. Now the reaction mechanism was studied in great detail at AS level. So we're going to test your understanding now of this mechanism and this reaction with some practice questions. So now we'd like to test your understanding of this reaction with some practice questions, and we have 3 for you to attempt. The first 2 are on this slide and the third question is on the next slide. So read through the questions, pause the video, have a go at the first 2 questions, then we'll have a look at the third question and then we'll go for the answers. So here's question 3. Once again, pause the video, have a go at the question, and then we'll go for the answers to questions 1, 2, and 3. So now let's go for the answers to questions 1 and 2. So question 1a is asking you to write a chemical equation for ethane and bromine. So ethane is C2H6, bromine is Br2 because halogens are diatomic. And I would get a substitution reaction, so I would get C2H5Br and HBr. Now you could write these out in full structural formula, that would be absolutely fine, or you could write shortened structural formula, so you could put bromoethane as CH3CH2Br, either would be fine. Now for question 1b, I would have propane and chlorine, so propane is C3H8, chlorine is Cl2, and this would make C3H7Cl plus HCl. And once again, I could draw out the compounds in structural formula or shortened structural formula. So question 2 is asking for the definition of the term free radical. Now a free radical is a species which has an unpaired electron. So this could be a molecule, an atom or an ion. And if we want an example of a free radical, a chlorine atom would be classed as a free radical because a chlorine atom would have 7 electrons in the outer shell and therefore it would have an unpaired electron. So a radical, a free radical, is a species which has an unpaired electron. So question 3 is asking you to draw the reaction mechanism. So this mechanism starts with an initiation step. And this is where the radicals are made. So initiation involves a chlorine molecule, Cl2, breaking homolytically. And this is caused by UV light. This supplies the energy for this bond to break. And homolytic bond fission is bond breaking that forms radicals because each atom in the bond retains its own bonding electron. So when the chlorine molecule breaks, I end up with 2 chlorine radicals. So I produce 2 chlorine radicals, and the energy to break this bond has come from the UV light. So UV light breaks a chlorine molecule homolytically to form 2 chlorine atoms or radicals. Now in the second step, propagation, a chlorine radical, a chlorine atom, reacts with a methane molecule to form a CH3 radical and HCl. And this is a 2-step process, propagation, because the CH3 radical can react with chlorine to form CH3Cl and a chlorine radical. So the chlorine radical has been regenerated, so it can go on and react with more molecules. Now the last step is a termination reaction, and this is where radicals join up, and this has to exist, otherwise the reaction will never end, because each radical will keep reacting with more molecules. So therefore, in a termination reaction, 2 radicals join up. So in the case here, we have 2 CH3 radicals that could join to form a molecule of ethane, or we could have a CH3 radical reacting with a Cl radical, and that would form CH3Cl. Or I could even have 2 chlorine radicals forming chlorine gas. So this is what the mechanism looks like. Now the propagation step can repeat many times, and this would allow you to have dichloromethane and trichloromethane and tetrachloromethane. However, I'm just going to draw the mechanism here with initiation, 2 propagation steps and a termination step. So halogenoalkanes can also be made from alkenes, and an example of this is shown on this slide because we have ethene reacting with hydrogen bromide at room temperature, and our product would be bromoethane. Now this reaction is an addition reaction because 2 reactant molecules join together to form a single product, and this reaction is classed as an electrophilic addition reaction, and this is another reaction that is studied in great detail at AS level because it's one of the mechanisms that you have to learn. Now a third way to make a halogenoalkane is from alcohols. Now there are a number of different ways this can be achieved, and we will discuss these when we study the alcohols topic. However, one way you can convert an alcohol to a halogenoalkane is to use a chlorinating agent such as phosphorus 5-chloride, sometimes called phosphorus pentachloride. Now if you react PCl5 with an alcohol such as ethanol, the OH in the alcohol is replaced with a Cl atom. And if we look at the equation, we have ethanol, C2H5OH, plus PCl5 makes chloroethane, C2H5Cl, plus POCl3, phosphoryl chloride, and hydrogen chloride gas. Now this reaction produces fumes of hydrogen chloride gas, and it's a very vigorous reaction. So therefore chemists have used this in the past to test for an alcohol group, because the addition of PCl5 produces fumes of hydrogen chloride gas in a very vigorous reaction. Now it's very common in exams for you to be asked how to convert an OH group into a Cl group, and PCl5 would do this as it's a chlorinating agent, and it could be used with other compounds, not just alcohols. If there's an OH group present and you react it with PCl5, the OH will change to a Cl. So now let's test your understanding of these 2 preparation methods with some practice questions. Read for the questions, pause the video, have a go at them, and then we'll go for the answers. So now let's go for the mechanism of the reaction of hydrogen bromide with propene. So first of all, I'm going to draw a propene molecule. Now I have to remember that there are 2 possible products when you add HBr to propene, but the major product that I get is 2-bromopropane, not 1-bromopropane. So I have to bear this in mind when drawing the reaction mechanism. So I'm going to draw in my propene molecule, and then I'm going to draw a HBr molecule with a delta plus hydrogen and a delta minus bromine, because there's a dipole here because bromine is more electronegative than hydrogen. And I'm going to draw a double-headed arrow from the middle of the double bond towards this delta plus hydrogen. And this will cause the hydrogen bromide bond to break. So I'm drawing another double-headed arrow here. Now when the pair of electrons moved from the double bond, this pair of pi electrons, it forms a dative bond with the hydrogen from the HBr. And therefore I'm going to draw my intermediate with a CH3 group bonded to a positive carbon, because remember electrons have moved away from this middle carbon. I'm going to then have a CH3 attached to this carbon, because remember it was CH2, but a dative bond has formed between the pair of electrons from the double bond, the pi electrons, and the H plus from the HBr. And therefore I have an intermediate which is classed as a secondary carbocation, because there's 2 alkyl groups attached to the carbon with a positive charge. Now the Br minus that's been formed when the HBr bond breaks has a pair of electrons that can move towards this positive carbon on the intermediate and form a dative bond, and I'm left with a final product of 2-bromopropane. Now the reason that I get 2-bromopropane and not 1-bromopropane is because the intermediate I've drawn here, which gives me 2-bromopropane, is a secondary carbocation, a secondary carbonium ion. And this is more stable than the primary carbocation or carbonium ion that would give me 1-bromopropane as a product. So that's the reason I get 2-bromopropane, is because the intermediate that's formed in the mechanism is more stable than the intermediate that would give me 1-bromopropane. Now this reaction is classed as an electrophilic addition reaction. Now notice that the reaction starts when a pair of electrons move towards a delta H+, that bond breaks and we've created an electrophile. So it's an electrophilic addition reaction. And it's an addition reaction because 2 molecules have joined together to form a single product. Now the mechanism is worth 3 marks here. 1 mark is given if you have all the arrows correct in the first diagram here. So in other words, a pair of electrons moving from the double bond towards the delta plus hydrogen, and then the bond between the H and the Br breaking with a double-headed arrow moving from the middle of the bond to the Br. There's 1 mark for that. Now if you had the arrows correct in the second diagram, in other words, an arrow from the Br minus moving towards the positive charge, there's a mark for that. And if you had all the charges correct in the diagram, so in other words, the Br minus having the charge on the Br minus correct, having the positive charge on the intermediate correct, that gets you the 3rd mark. Now if you classified the reaction correctly as an electrophilic addition, there's a mark for that. And for part C, there's 2 marks available. You get 1 mark if you said that 2-bromopropane forms a secondary carbocation as an intermediate. There's 1 mark for that. And if you said that secondary carbocations are more stable than primary carbocations, there's a mark for that. So now have a go at question 2. Read through the question, pause the video, have a go at it, and then we'll go for the answers. So now let's go for the answers to question 2. So for part 2a, you're asked to write a chemical equation to describe the reaction between propan-1-ol and phosphorus 5-chloride. So there's 1 mark for this. So propan-1-ol is CH3, CH2, CH2OH plus PCl5 here makes chloropropane, 1-chloropropane, so that's CH3, CH2, CH2Cl. And my other 2 products are POCl3 and HCl. So there's 1 mark for that. Now I could draw full structural formula for the organic compounds here if I prefer, or I could do shortened structural formula like I've done in this equation. Now for part B, it says propan-1-ol is replaced with butan-1-ol. Name the halogenoalkane that would be produced. Well, if I replaced propan-1-ol with butan-1-ol, the halogenoalkane that I would produce would be 1-chlorobutane, and there's 1 mark for that. For question 2c, I'm asked to draw the structural formula of the organic compound that would form if PCl5 is reacted with ethanoic acid. Now PCl5 is a chlorinating agent and it converts OHs to Cls. So all I have to do is draw this molecule and replace the OH with a Cl, and if I draw this I would have a CH3 bonded to a C double bond O and a Cl. Now this is called ethanoyl chloride and it's a member of the acid chloride or acyl chloride homologous series, and we will study these later in this module. So now let's turn our attention to the properties of halogenoalkanes, and by properties I mean physical properties. Now halogenoalkanes have properties that are similar to the parent alkanes. So for example, chloroethane would have similar properties to ethane. Now they are colourless, they're relatively odourless, and they're hydrophobic. They don't dissolve very well in water. Now the strong polarity of the carbon-fluorine and carbon-chlorine bonds will give rise to attractive forces between dipoles of neighbouring molecules. So they will have permanent dipole intermolecular forces. And this is why the chloro and fluoroalkanes will have higher boiling points than alkanes, because alkanes will have temporary dipole forces between the molecules, and fluoroalkanes and chloroalkanes will have permanent dipole intermolecular forces. And these permanent dipole intermolecular forces are stronger than the temporary dipole forces between alkane molecules. Now in terms of bromoalkanes and iodoalkanes, these molecules are less polar. However, a bromine atom and an iodine atom are much bigger atoms than a hydrogen atom and a fluorine atom and a chlorine atom, and therefore there are more electrons in these atoms, and therefore there are more van der Waals forces, there are more temporary dipole forces between these molecules, these bromoalkanes and iodoalkanes, and therefore the boiling points of these molecules are also higher than alkanes due to the fact that their halogen size is bigger, there are more electrons, and there are more van der Waals forces. Now the second property we're going to look at is solubility. Now halogenoalkanes, although they're polar molecules, they have a low solubility in water. This is because although they're polar molecules that can interact with water molecules, the attractive forces set up are not as strong as the hydrogen bonds present in water. So, although they dissolve a little bit more than alkanes, they're only slightly soluble in water. Now, water prefers to bond to itself. The hydrogen bonds that form between water molecules are a lot stronger than the bonds that would form between a water molecule and the halogenoalkane. So you have to remember that halogenoalkanes don't dissolve that well in water because the dipoles are much weaker than, say, an OH or an NH, and therefore these molecules tend to dissolve better in non-polar solvents. So now let's look at the uses of halogenoalkanes. So the first use is as a solvent, and halogenoalkanes contain a polar part of the molecule, the carbon-halogen bond, and a non-polar section of the molecule, the alkyl chain, and therefore they can mix with a variety of polar and non-polar organic substances and are therefore used as solvents. And halogenoalkanes, as they are non-flammable, they tend to be used in applications such as dry cleaning and other processes involving degreasing, so they are very good solvents. Now, a second use of halogenoalkanes is in anesthetics, and one of the earliest compounds used was trichloromethane, and to this day compounds such as halophane are still used in surgery. Now, halogenoalkanes are also used in refrigerants and also in air conditioning, and liquid halogenoalkanes are easily evaporated to form gases. They tend to have boiling points not too far away from room temperature, and therefore the heat energy needed to turn the liquid to a gas can be removed from a fridge, and this then is used to cool the contents of the fridge. And once again, non-flammability and non-toxicity, as well as having a suitable boiling temperature, are reasons why they have these uses. Now, you also have to be aware that the use of halogenoalkanes is regulated internationally. And this is because some halogenoalkanes have found to be toxic, for example, polychloroalkanes, but mainly because chlorofluorocarbons, CFCs, cause damage to the ozone layer. So there's been a number of international treaties that have been signed by countries to reduce the use of CFCs, chlorofluorocarbons, because of the damage they do to the environment. Now, damage to the ozone layer allows harmful ultraviolet rays to reach the Earth's surface and can cause skin cancer. And if you look at the table here of bond strengths, you can see that a carbon-chlorine bond breaks a lot easier than a carbon-hydrogen and a carbon-fluorine bond. And therefore, CFCs, if they come in contact with UV light, the carbon-chlorine bonds will break and they will form chlorine radicals. And these chlorine radicals can break down ozone into oxygen and therefore break down the ozone layer. And this ozone layer is protecting us from the harmful UV rays. Now, because CFCs are relatively unreactive, they can last in the environment for a long time and they can diffuse into the upper atmosphere. And if they diffuse into the upper atmosphere, the UV light breaks down these CFCs into radicals, and these radicals, these chlorine radicals, can break down the ozone into oxygen. To help us understand how CFCs cause ozone depletion, I'm going to look at the mechanism. So the first stage of the mechanism is initiation, because ozone depletion is a radical process. And I'm going to draw a CFC, and this has got 2 chlorines and 2 fluorines on. And the carbon-chlorine bond is going to break, caused by UV light, to form free radicals. And this is homolytic bond fission. So I will be left with CF2Cl radical. And my other product will be a Cl radical. Now this Cl radical can react with ozone in the next step, which is called propagation. So if we have our Cl radical here and it reacts with a O3 molecule from the ozone layer, I will end up with ClO radical and oxygen. And then this ClO radical can react with more O3 to produce 2 molecules of oxygen and a Cl radical. So this Cl radical has been regenerated and can keep on decomposing ozone to O2. So overall, I have O3 ozone breaking down into O2. And when this happens, the ozone layer is being depleted and the ozone layer is protecting us from harmful UV rays which cause skin cancer. Now, alternatives to using CFCs would be to use compounds that don't contain a carbon-chlorine bond. So I could use HFCs because they only contain CH, CC and CF bonds, and these are a lot stronger than the CCl bond, and therefore they don't break down into radicals, and therefore they won't cause ozone depletion. So we're now going to test your understanding of this with some practice questions. So here's our first practice question. Once again, read through the practice question, pause the video, have a go at it, and then we'll go for the answers. So our first practice question is asking why fluoroethane has a higher boiling point than ethane, and this is worth 2 marks. So this is all to do with the intermolecular forces that exist. So fluoroethane contains a dipole, a delta plus carbon and a delta minus fluorine, and therefore it has permanent dipole intermolecular forces between its molecules. So if you said that, there's 1 mark, and these are stronger than the temporary dipole forces that exist between molecules of ethane. So if you said that, you get the 2nd mark. So here's our second practice question, and this comes in 2 parts, 2A and 2B. Here's part 2A. Read for the question, pause the video, have a go at it, and then we'll look at question 2B. So here's question 2B. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers to both 2A and 2B. So question 2A is asking you to outline the adverse environmental effects of using CFCs. So if you said that CFCs produce chlorine radicals, there's 1 mark for that. If you said that these destroy the ozone layer, there's 1 mark for that. If you then said that the ozone layer protects us from UV radiation, there's 1 mark for that. And if you said that UV radiation causes skin cancer, there's a mark for that. So 1 mark for each of those points, a total of 4 marks. So question 2B is asking you to use the following data to explain why hydrofluorocarbons, HFCs, have replaced CFCs in many of their uses. Now, remember that CFCs cause damage to the ozone layer because the carbon-chlorine bond breaks when the CFC comes into contact with UV light. Now, if you look at this table, you'll see that in HFCs there are CC bonds, CH bonds and CF bonds. And this table shows you that those bonds are a lot stronger. They need more energy to break than a CCl bond. So for 1 mark, you would have to say that the CF, CH and CC bonds would need to be broken to form radicals. It's getting that idea across. That's 1 mark. And if you said that these are too strong to be broken by UV radiation, that gets you the 2nd mark. So that concludes this video lesson. So after watching this video, you should now be able to describe how halogenoalkanes can be prepared from alkanes, alkenes and alcohols. You should be able to understand the intermolecular forces present in halogenoalkanes and how these are linked to physical properties such as boiling points. And finally, you should be able to describe the main uses of halogenoalkanes and why their uses are restricted due to toxicity and adverse environmental impacts. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @RadaChemistry.